Hello, I'm DC Eagle of NASA's Jet Propulsion Lab. We're here to talk about the science of the GRAIL mission to the moon. Here to talk about GRAIL, we have with us today Bobby Fogel, GRAIL program scientist, NASA headquarters, Washington. Maria Zuber, GRAIL principal investigator, Massachusetts Institute of Technology, Cambridge. Sammy Asmer, GRAIL Deputy Project Scientist, NASA's Jet Propulsion Laboratory. And Lisa Hubbard, Teacher in Residence, Sally Ride Science, San Diego. And we'll open it up with Bobby Fogel.
Thank you, DC. You know, they say that you can't judge a book by its cover. But you know, virtually every planetary mission to one of the inner planets, the rocky bodies of the solar system, Mercury, Venus, the Moon, and Mars, has done just that. They've gone to investigate the planetary cover or the planetary surface/atmosphere. It's not that scientists aren't interested in the planetary interiors. On the contrary, we've known for some time that the interior of planets holds the secret to their formation, evolution, and internal processes. The problem is that investigating the interior is one of the hardest things to do in space science. Consequently, we go to places where we can actually access, which is the planetary surface, and we look there for clues as to what's going on in the planetary interior. Can I have the animation, please? Case in point, the moon. This little animation shows you a little comic of the various different missions that NASA and other space agencies have sent to the moon over the last 50 years. Every single one of them, without exception, has focused as its main goal to understand the surface of the moon or some property at the lunar surface, such as radiation. Not one of them has really had as its focus the internal composition or structure of the moon. Imagine for a second what the state of medical science would be without the MRI, the CAT scan, the X-ray, or the scalpel. Everything that you know about the internal workings of a human being would have to come from observing their skin, their eyes, their hair. And you'd have to use those observations to try to figure out what's going on inside a person. Pretty primitive, eh? Well, by analogy, this is the state of our understanding of the lunar interior and the interiors of the rocky bodies at this moment in time. So you can imagine our delight at NASA headquarters when we selected in 2007 for the Discovery mission, the GRAIL mission, which is a mission to the planetary interior of the moon. Now, why do we care about the lunar interior? Well, 4.5 billion years ago, after the moon formed, it started heating up due to planetary impacts by asteroids, meteorites, and comets. The heating also came from the breakdown of radioactive elements inside the moon. And eventually, the melting point of the moon was exceeded, and a giant ocean of magma was formed. This magma ocean was lunar-wide and extended down to depths at least as great as 400 kilometers, maybe more. Now, out of this magma ocean, eventually, as it started cooling, crystals or minerals started forming. Those minerals that were denser than the surrounding liquid sank, and those that were lighter than the surrounding liquid floated. You know, you see a manifestation of this every time you look up at the moon. The face of the moon that shows itself to us, you see white areas and dark areas. The white areas are composed predominantly of a rock type called anorthosite, and anorthosite is dominated by a mineral called anorthite. Now, anorthite was lighter than the surrounding magma ocean, so it floated and created the lunar highlands or the lunar crust. Now, eventually, the magma ocean fully cooled, and tectonic forces took over and shaped the moon and its interior even further. And eventually, there were basin-forming impacts, and there were flood basalts going into some of the mare. So the moon has a lot of structure. And this is where GRAIL will make history. GRAIL will be the first mission to actually go to the moon with its primary focus of determining the structure and composition of the internal parts of the moon. Now, to be sure, we've used gravity science before to try to gain some insight as to what's going on inside the moon. However, these have been very primitive attempts compared to what GRAIL will be able to accomplish. If those previous attempts could be likened to a magnifying glass, GRAIL, by contrast, would be a high-powered microscope. So we're delighted that we're here and we're one day away from launch. GRAIL is ready, it's on time and on budget. Now if the weather would cooperate, we'll have a great mission. Maria?
Thank you very much. I'm thrilled to be here, thrilled to be at this state one day before launch. And let me tell you a little bit about the science of the GRAIL mission. If I could have the first graphic, please. That's a picture of the near side of the moon as we view it from Earth. Nearly every human in history has looked up and seen that sight. Aside from the sheer beauty of seeing the moon in the night sky, that moon's surface holds the record of the whole history of the evolution of the moon. A great deal of what you see on the lunar surface, however, has been controlled by processes that have occurred inside the moon. The next slide. So we've learned a lot about the surface of the moon from orbital reconnaissance, and we've had the fortunate situation of having 12 humans who've walked on the surface of the moon, who've returned samples. These samples have been analyzed for the past 40 years. They are still being analyzed today using the newest techniques, and they are still providing us with information. So we have orbital reconnaissance of the surface. We have lunar samples, which we can analyze in Earth labs. The piece of the puzzle that has been missing in trying to reconstruct lunar evolution has been a good understanding of the interior, and that's what GRAIL hopes to provide. So in the next chart, I'd like to talk a little bit about what are some basic things about the moon that we don't understand. Okay, this is a beautiful wide-angle camera images of the near side of the moon on the left. That's the side that we see from Earth. And on the right-hand side, that's the far side of the moon. So as Bobby mentioned, we have on the near side of the moon bright areas, lunar highlands, which are areas that have melted, and light crystals that have floated to the top. As these cooled off, large impacts battered the surface of the moon. It was the material that was left over from accretion. And then basaltic magma, lavas, flooded these large impact basins. If you look at the right side, you don't see these magmas. And we used to think that there was melting underneath the near side of the moon, and that flooded the impact basins. But on the far side, we didn't have these basins. So the backside of the moon melted in the interior, but the material was never able to rise to the surface because of the lack of large basins. But if you look at the next-hand slide, this is an elevation map of the moon that was collected from observations from the laser altimeter on the Lunar Reconnaissance Orbiter, which is mapping the moon right now. In this map, white and red correspond to high elevations, and blue and purple correspond to low elevations. So if you look at the left-hand side, the dark blue areas, you can see that these are actually low areas that were flooded by magmas. But now if you look at the vantage point of the third dimension, on the right-hand side, you see that, the backside of the moon has the largest and deepest impact crater on the planet, but yet this never got filled by magma. So what that tells us is that what happened on the near side of the moon in the interior was quite different than what happened in the far side of the moon. The backside obviously didn't melt. And so that's a fundamental question which has shaped the surface of the moon, which has eluded our understanding. Now, if we could go back to the graphic of the elevation map, that bright white area there near the equator, very recently an idea has come out where we might not have had one moon, but that originally two moons formed around the Earth, that a small lunar companion formed in orbit around the Earth, in the same orbit as the moon, but ahead of it or behind it, and that very slowly, over early time, this second moon would have collided with the first moon, but it would have done so at such a low velocity that it would have added more material to the moon than it ejected. And this would actually have caused a mountain to form rather than a crater. This is a very new idea, and it made specific hypotheses for what the inside of the moon should be like if this occurred, and these ideas can be tested with the GRAIL mission. If we could have the next slide, please. This is a cross-section of our state of knowledge of the deep interior of the moon. On the left-hand side is the near side, as we view from Earth. The right-hand side is the far side that we never see. The purple areas correspond to zones on the front side of the moon where Apollo astronauts left seismometers, which probed the interior. You can see in the dots there are some shallow moonquake locations, and you can see that there are some deeper moonquake locations shown by the white dots that are deeper there. These deeper moonquakes, they tend to be triggered by tides. We don't know why the moonquakes occur at those depths and not shallower depths. We don't know whether there are shallower moonquakes that we're not detecting. We suspect there are. We don't know anything about seismicity on the far side of the moon that would tell us perhaps the structure of the near side versus the far side and why they're different. The next slide, please. Okay, here's a cross-section of what we think the deep interior of the moon might look like. Information from the Apollo seismometers that is still being analyzed today, and from lunar laser ranging, where laser stations on the Earth shoot lasers up to retroreflectors that the Apollo astronauts left every month and tell us about wobbles that give us information about the subtle structure of the interior of the moon. The suggestion is that the moon has a very small, solid iron core that's surrounded by a liquid iron core, but we don't actually know for sure that that's the case. It's actually quite possible that deep inside the moon, the core could be titanium oxide, which is a material that would have fallen out or condensed out of the, crystallized out of the magma ocean and sunk to the deep interior of the moon. And we certainly don't have a good idea about the thermal state. We think liquid iron could be melted for the outer core. It's not out of the question that the parts of the deep lunar mantle are actually molten. And of course, if we want to try to reconstruct the evolution of the moon over time, we certainly need to be able to reconstruct the temperature structure of the moon right now. So if we could go to the last graphic. So in summary, what we're trying to do is, with the GRAIL mission, we're essentially getting a picture into the interior of the moon, which we intend to combine with the plethora of orbital observations that have been taken of the surface and are being taken of the surface today, and to combine those with the treasure of the lunar samples that we continue to analyze. And from those collective observations, we intend to provide a holistic view of the origin and the evolution of the moon, and by extension, how other rocky planets in the inner solar system formed. And with that, I'll turn it over to Sami Asmar to tell us how we're going to execute this mission.
Thank you. The team of scientists and engineers at all the institutions affiliated with the GRAIL mission have worked hard to ensure that the technique we've selected to conduct the science investigation and the design of the flight system, ground system, and mission operation systems meet the science requirements, in some cases with plenty of margin. I'm going to talk briefly about the technique and the design after hearing about the science scenarios. So if I can have the first animation slide, please. Once at the moon, the two GRAIL spacecraft will orbit at a very low altitude, and we detect the gravity field by precisely measuring the changes in the distance between the two spacecraft. So as the two spacecraft orbit, and this shows that the resulting gravity map of the moon. As the two spacecraft orbit, in this simple scenario, they approach a gravity load, such as a mountain, that pulls on the first spacecraft and increasing the distance. Then the second spacecraft will sense the same gravity, and the distance will decrease. And then as they move forward, the trailing spacecraft will sense the same gravity and the distance will increase again. So there's a dance going on between the two spacecraft as they orbit every little features of mountains and craters. Now, at the end, the resulting gravity field is really result from after putting all this data in one big blender and a lot of processing, and we get a high-resolution gravity field of the moon. Next slide, please. This slide shows that we actually can tune our instrument to different targets, such as the local and regional features of the moon, small craters and mountains, all the way to the big global picture in which we look for core and tidal effects. The way we tune our instrument is by changing the separation distance between the two spacecraft. So we start low altitude and close distance, and then we increase the distance and raise the altitude, and that will automatically make us more sensitive, optimize the sensitivity to the global features. Next slide, please. This shows the mission design from launch to orbit insertion. We have several months, actually, which we use very effectively. In addition to navigational aspects, on the science side, we benefit from the long cruise period by having the spacecraft outgas in the vacuum of space and having our clock drift stabilize. Next slide, please. This shows the radio complexity of the mission. So the two spacecraft have two types of radio signals going back and forth between them, Ka band, or 32 gigahertz, and that measures the changes in the distance very precisely, and S band, which is a time synchronization exchange of information. When the two spacecraft are then in view of ground stations, they dump or telemeter the information to the ground. Next slide, please. This graphic I'm using to impress upon you how sensitive we are to non-gravitational forces, even stuff we can take for granted, such as solar radiation pressure, sunlight. So we had to design the surface properties of the spacecraft to account for solar radiation pressure. We are a gravity mission, so every force acting on the spacecraft is a big factor. So we don't want to mistake non-gravitational forces for actual features from the moon we're investigating. And then the next slide, we show two other actually features, just reflection of sunlight from the surface of the moon, and when the moon is in the shade, the IR, infrared radiation from the moon. These also constitute non-gravitational forces that we care about measuring and calibrating. The last slide, please. Dr. Ed Weiler of headquarters called GRAIL a physics mission, and this slide really shows that it is indeed an intersection of two branches of physics, mechanics or dynamics and electromagnetism. This graphic shows if a spacecraft is orbiting a body, a planet, moon, the moon, Mars, and we fly over a gravity feature, the spacecraft will literally get pulled towards the feature, and that effect gets manifested as a Doppler shift in the electromagnetic signal. If it flies over a valley or absence of material, it will slightly get repelled. So this shows the beauty of gravity science or radio science, where we actually investigate mechanical forces acting on the spacecraft via electromagnetic effects. And now I'll pass it to Lisa.
Great. Good morning. It's an exciting time to be here at the Cape, and you can feel the buzz of the excitement start to increase today as we're narrowing down the time to launch, and hopefully this time tomorrow we'll be on our way to the moon. I'm here to explain to you about the education and public outreach component of GRAIL, which is called GRAIL MoonCam. It is led by Dr. Sally Ride, America's first woman in space, and her full team at Sally Ride Science in San Diego. One of the unique things about this mission is it's NASA's first planetary mission to include instruments that are fully dedicated to education and public outreach. And we intend to tap into that excitement of science and technology using the context of lunar exploration. While GRAIL is in orbit and it's doing its gravitational experiments, MoonCam will serve as eyes on the moon for students. Next slide, please. We will do this using cameras. There will be 4 cameras on each spacecraft. There are 2 that are pointing forward and aft at a 60-degree angle, and there are 2 that are pointing directly to the surface, and those will be different powered lenses. This program is available at absolutely no cost to schools or to students, and students will have the opportunity to use those cameras to take their very own photographs of the moon. Once the spacecraft are in orbit, the cameras will be activated, and this portion of the mission will last approximately 80 days. Our Mission Operations Center, which would be similar to Mission Control in Houston, is located at the University of California, San Diego. And there we have undergraduate students that have taken part in the planning and the operations of this mission. And during the actual mission, the MoonCam phase, they will serve as a link to students worldwide. Students will determine what photographs they want to take by accessing the website. Slide, please. And there are various ways that they can choose their location. Just like we learn in different ways, there are different ways that they can approach it. This slide shows the latitude and longitude, which spacecraft will be orbiting at what times. Next slide. And it's also very interactive. Students will be able to zoom in on the moon. They'll be able to rotate it. They'll be able to look at both of the ground tracks of the orbiters, and they can simply click on the ground track and decide, it will give the information like latitude and longitude, and let them decide where they want to take their photographs. Once they have made that decision, they'll send their request into our Mission Operations Center there at University of California, San Diego. And there our undergrad students will help facilitate that. And then the images will be available in a gallery on the website. Students will be able to go back later and identify exactly which picture that they took. They'll be able to annotate their images. They'll be able to use them for further investigation. They will have access. Matter of fact, the general public will have access to all these images. They'll be able to access other student photographs as well to further their investigations. Both before, during, and after the mission, Sally Ride Science is providing support and training for educators. We're linking them up with lunar scientists. We're helping them with hands-on activities that address the standards that educators have to meet in their classrooms. But more than meeting those standards, this is something that's going to be a lot of fun for the students. And engaging in real-world science is going to help not just to help us develop scientifically literate citizens, but hopefully to encourage students to enter careers that have to do with science, technology, engineering, and mathematics. And you never know what the wow factor is going to be for a student. And besides the areas of science and technology, you never know what an image might evoke out of a student as far as maybe art or poetry or maybe even music, which are things that we often tend to forget about combining with science. It's difficult for us to measure the impact of inspiration, but NASA does have that inspiration factor, and our students certainly need that, and it's something they can get excited about, and it's going to give them their own ownership of these images, which it's been my experience that kids get really jazzed about. I would encourage you, next slide, to go to our website at www.mooncam.ucsd.edu. And we would like educators to go there and register. We would like the general public to go there and read up and become more informed and get involved. It's also very timely to let you know that we now also have an app for GRAIL MoonCam. It is free on iTunes. You can go there and you can download it. And once images start coming in from MoonCam, you'll be able to view the images there through that app. You'll also be able to track the spacecraft during the mission. And we're also, GRAIL MoonCam is available on Facebook. So we'd hope you go and check that out, and on Twitter. So I hope you'll come along with us on this journey. Thank you.
Thank you, Lisa. We'll open it up to questions here from the media at the Kennedy Space Center press site. Please state your name and media affiliation. Marcia?
Marcia Dunn, Associated Press. The 82-day science phase, when exactly does it begin via calendar? And might it move up sooner if you get your orbits precise enough, quick enough?
Okay, March 8th, I believe, is the day. Okay. So the 82-day science phase is, the beginning of that is based on both how long it takes the spacecraft to get into their lower circular mapping orbit and then line themselves up so that they start to range to each other. But it is also based on when the sun angle to the solar panels provides enough sunlight to power them. So if all goes well, it's possible that that could be somewhat earlier. However, of course, we're taking the conservative approach of making sure that it operates well. Okay.
The chart with all the moon missions over the decades. I believe you said at a previous briefing that was 109, but I can't remember the number, and that includes Apollo landings as well. How many of those 109 missions actually studied the far side of the moon? I'm just wondering how much still is to be learned about the far side.
Okay, so let me think about that. Okay, so I don't know the exact numbers, but I can call it out to what happened. So the early reconnaissance missions to the moon went into an equatorial orbit around the moon because they were interested in doing reconnaissance of the far side equator, which was the easiest place to get to the astronauts to energetically, okay, from an energetics standpoint. So, so information was gained about the equatorial area of the far side, and there was very little information in polar orbit where you would be getting the whole far side. So there was, I know there was one lunar orbiter that did that early on, but and actually there was a Soviet Zond orbiter that also, but very little. And then the more recent missions to the moon, however, Lunar Prospector and Lunar Reconnaissance Orbiter, they of course are in a global. So there has been some information, but in terms of studying the interior, there is a vast amount to learn because other missions have studied lunar gravity, but because of the moon being in the unusual position where it's in synchronous rotation, where we only see one side, the way that we typically measure planetary gravity is to track the radio signal of a spacecraft in orbit while the planet rotates under the spacecraft. But if you never see the far side of the moon, you can never track it directly, and so the two spacecraft have to use that so that they can track each other.
Hi, Irene Klotz with Reuters for Dr. Zuber. You mentioned that one of the scenarios for the core of the moon is that it might have titanium oxide, and I was just wondering how, once you get these measurements from GRAIL, you're going to be able to distinguish between the different materials and how much of each might be, and just how precisely you anticipate being able to definitively know what's inside the moon.
Okay, so first of all, gravity is a potential field measurement. So you can come up with many different compositions that could satisfy the gravitational field that you measure, which is why you never want to analyze gravity or magnetics or any other potential in isolation. So the value of analyzing the gravity data is that we have a great deal of compositional data from the surface, which allows us to zero in on the bulk composition. And what we will be able to do about the deep interior is greatly reduce the error bars in what the radial distribution of mass is and combine that with models of the bulk composition. And from that, we expect to be able to distinguish iron versus not iron, something like titanium oxide. Okay.
And over to Bill Harwood.
Bill Harwood, CBS. I have three questions. One is, just for the sheer precision of your experiment, can you guys give me some sense of, like your graphics show, little dips and little rises over, what's actually happening to the spacecraft in terms of the real dimensions? Is it dropping a meter? Is it dropping a few inches? And can you tell me a little bit about the accuracy of the distance measurement required? In other words, at 100 kilometers, how much is it actually, what's actually happening?
So if over the distances between the two spacecraft, which range between 65 to 225 kilometers, we are sensitive to changes down to 1 micron. So that's really on the order of a size of a red blood cell. That's how accurate the measurement of the distance is.
And the up and down that it's doing as it goes over mass cons or mountains or whatever?
Well, that was just an abstract illustration. Exactly.
Okay.
Yes.
And for Dr. Zimmerman, the heat of the core of the moon after this much time, is that radioactive? Does it keep it hot? It would keep a liquid core? I mean, what's keeping it liquid?
Yeah, it's well, there's several contributions to the heat. Part of the contribution is the potential energy of the infalling material as it accreted the moon. So there would be some accretional heat that would be left over, and the rest of the residual heat would be due to the decay of radioactive elements. So Bobby actually talked about the fact that the exterior of the moon, we think it largely melted, and the big heavy elements like uranium, thorium, potassium that are the heat-producing radioactive elements, those are actually the heaviest. And so the idea is that they may have sunk partway into the moon. They may have conceivably sunk all the way to the core, where they would be providing this residual heat. And actually, one of the interesting conundrums is that we think that the moon is molten in the deep interior today due to these heat sources. Yet, despite the fact that the moon early in its history we believe was molten on the exterior, it looks like the surface cooled off extremely fast because of the large size of the gravity anomalies that we see over those near-side basins. So there was, we used to think, so the near-side basins have lava flows that are more dense than the surroundings. And we thought that if we could subtract away the gravitational attraction of those lava flows, that we would see no gravity anomalies. But in fact, we've had near-side gravity before, and we've done that, and there's still whopping anomalies. And what that means is that at least on the near side, the moon on the outside cooled off fast enough so it was able to maintain strength. And so we have this odd situation where the deep interior of the moon still looks like it's hot, but the outside that we know was molten cooled off apparently much more rapidly than the models would indicate. So it's a fascinating topic, a fascinating question in planetary evolution.
And one more quick one from me, I'm sorry. The second moon theory that you were mentioning to us, I'm assuming, or I don't know what I'm assuming, but was this a small body that then accreted on the far side and that made the highlands, or is this a larger body that deposited material and then somehow left the scene?
The simulations show, so the authors ran a range of simulations, and the simulation that they interpreted that worked, so to speak, to produce the far side highlands is one where you have a moon that's about a third of the size of the new moon, slowly drifted and stuck. Okay, and so there may be other scenarios for making this happen. And it's such an exciting idea. I'm guessing the modelers are hard at work right now trying to find whether there are different scenarios that might explain that in an alternative way.
Todd?
I'm Todd Halverson of Florida Today, probably for Sammy. Is there a planetary window associated with this launch? In other words, how many days do you have to get this launch off the ground, and what happens if you don't fly in that window?
Geometrically speaking, we have about 42 days to launch, but I think from a practical point of view, it's down to 30, 32 days, having to do with fueling the rocket for a limited period. If we miss the entire opportunity, then we would have to wait on the order of 6 months, so that when we arrive, we avoid solar eclipses at the spacecraft on the moon.
Thanks. And this one's probably for you, too. I was wondering if you could discuss the low energy trajectory that you're taking to the moon, why it was selected, and whether your arrival date at the moon would change if the launch was pushed back a week or 30 days or whatever.
So the low energy trajectory was selected basically to save on cost. So you do not have to use a bigger rocket to get you to the moon faster. But also, even if you do that, you would need, once you arrive at the moon, you would need to brake to reduce that velocity, and that would require carrying additional fuel on board the spacecraft. So this avoids that entire problem and also gives us this flexibility. So we arrive at the moon on New Year's Eve, then New Year's Day, regardless of the launch date. So that's a very nice flexibility in the mission design. And as I mentioned earlier, it turns out there are additional benefits to having a relatively long cruise period on the order of weeks to allow for outgassing of the spacecraft, clocks to stabilize, the operations team to learn how to fly the mission.
Right over here.
Hi, Ken Kramer for Spaceflight Magazine. For Maria, to follow up on this idea of the second moon proposal, I wonder if you could explain a little bit more about how GRAIL could help confirm this theory. And I'm also wondering, at these spots, do we know, is the composition different? Is that why we think the second moon
could have hit? Yeah, I'd be happy to address that. Okay, so because this second moon, this lunar companion, would have accreted from the same material that our moon formed from, it should have the same composition. Okay. However, because it's a smaller body, it should have cooled off more quickly than our moon did. All right. So one way to test this is to look at the crystallization age of minerals, of material in the lunar highlands there, compared to the crystallization age of lunar highlands away from that. However, there are no plans on the books right now to send a lander to the moon to bring back samples from those far side highlands to Earth, because you can't make that measurement in situ. That has to be done in a lab on Earth. So we need to actually bring samples back. However, what you can test, okay, with GRAIL is I told you that the idea was that the moon had a magma ocean, and it was light crystals of a mineral called plagioclase that rose to the top, and then heavy minerals such as the uranium, thorium, potassium, they would have sunk, and as this companion accreted to the moon, the simulations show that these heavy materials would have been pushed to the near side of the moon, and should have left a residual on the near side of the moon, which, because they're heavier, they would be detectable with gravity. So, and we have some idea of what the thickness of the magma ocean is, so we have some idea of the depth of where this residual density anomaly should be. So this is something that we can test very precisely. So it's very good hypothesis testing, because it made a prediction that can be tested with a mission that's upcoming.
Thanks. Just want to follow up. If you survive the lunar eclipse, I was talking yesterday with some of your colleagues. What's the possibility to extend this mission then?
Okay, I'll address that.
Sure.
Okay. Okay, so about every 6 months, there is a solar eclipse that causes the spacecraft to be in lunar shadow for several hours. Okay, and the spacecraft were not designed to make it through those eclipses, because we were designed to do the mission during that period. However, well-designed spacecraft often exceed the performance that you design them at. So if the two spacecraft made it through the lunar eclipse in June, and both of them would have to make it through, then what would have to happen is actually, because of the solar geometry, you'd have to move the back spacecraft to the front for ranging purposes, and you'd need to line them up again. And that would take, well, we think it would take less time than it took the first time, because the mission operations team would have a better idea how to analyze or how to operate the spacecraft. Then they could conceivably begin to range again. And there's another lunar eclipse, or another solar eclipse, excuse me, in December. That one, relatively speaking, is rather benign compared to the one in June. And so they could conceivably keep going. But if we were going to do that, we fully expect to achieve the mission objectives during the primary mission. And so we've been focused on achieving the primary objectives, which is the job of the team right now. And after we get the spacecraft on the way to the moon, we can begin to think about whether new science would be possible that would, enhance our understanding of the moon for a very small investment. And we're sufficiently under budget that we probably wouldn't even have to ask for extra funds to do this.
That was my last question, right? You said, well, they're going to provide you the money to then do that. Okay.
He shouldn't have to.
And I understand we have a call online.
Hi, thanks. Denise Chow at Space.com. Question for either Dr. Fogel or Dr. Zuber. Could you explain in more detail about how having lunar gravity maps could help with planning future either robotic or manned missions to the moon?
Well, if you have a very high precision gravity map, then it's a benefit to both to both human exploration as well as robotic exploration. You can get to your point better and more accurately and faster.
And then just as a follow-up, with yesterday's release of the LRO pictures of the 3 Apollo landing sites and then also this upcoming GRAIL mission, do you feel that these events will perhaps inject new public interest in the moon?
I hope so. The moon is a fantastic body in terms of its study, in terms of learning about early planets. It's nearby, it's accessible, and it preserves the record of what early planets were like. So the surface of the moon 4 billion years ago. Other planets in the inner part of the solar system have gone through the same processes that the moon has gone through, and because we've studied the moon so significantly and we're studying it, I actually think in the next 5 years we're really going to rewrite the book in our understanding of the early planets.
Also remember, the moon is your backyard. If you had a house, the moon would be the house next door, and the other closest planets like Mars would be miles away. So it pays to understand your nearest neighbor. And the moon has affected life on this Earth in many different ways, and I think the continuing studying of the moon is always going to be a profitable thing.
Great. And back here at KC.
Marcia NAP for Ms. Hubbard. Will your cameras be providing, like, streaming down live pictures, images of the moon? I didn't know if that was going to be possible to click on and see live views of the moon. And will the children, or will it be the team in San Diego, be actually taking the pictures? It wasn't who snaps the picture.
Okay. I believe that the students send the request to the Mission Operations Center, and then the Mission Operations Center is what actually takes, yes, the photograph. And what was the first part of your question again? I'm sorry.
Live streaming from the moon, pictures, images.
I'm not sure that we know that for sure yet. Do we?
Can I address that? So the way that we were able to get this experiment on the mission was to make it entirely best efforts. Okay, so the science mission must take place and must take priority, and then whatever data rate is left. So it's it's conceivable that we can string together some images and bring them down. They wouldn't be quite live because we're not going to take the extraordinary efforts that would be required to do live streaming video, but we could get conceivably some, enough images taken that we could make short videos.
So it would be somewhat recent.
Correct.
Yeah. Okay.
Yeah.
Thanks.
Thanks. Did you, any of you have an updated weather forecast for the morning?
I haven't had time to look at my email this morning, so.
Thanks. And also, just to follow on a little bit what you were saying earlier to Bill about the micron measurements, is it correct to say that a mountain would move one of the GRAIL spacecraft or both over time, just a micron, or would it be several microns for a mountain? And can you is there any way to kind of to say, like, match up a certain size feature with how much of an impact you think it would have on the spacecraft's altitude?
In fact, the amount of change in the range or the distance between the two spacecraft will depend on this load, the gravity feature. So if it's a small feature, it will move it a little bit. If it's a bigger feature, it will move it a lot. But the interesting part is that sometimes you'll see a big mountain and you would expect a high gravity signal, and then in reality you get no gravity signal. And that's where it gets interesting from the geophysics point of view, because the planet has compensated for the weight of this load and for a net zero effect. Or you fly over a flat region, and obviously you look at the topography and the images, and it's flat, you expect no gravity signal, but then our instrument will measure a gravity high. Again, another puzzle. Then it turns out there are mascons or subsurface buried features or higher density material that can only be probed through gravity. So it's a very complex and exciting science that way.
And to Bill for a follow-up.
It's really a follow-up to Denise's question earlier from space.com about the value of this data for future missions. I mean, you're talking about such subtle effects from these changes in gravity as a vehicle orbits. It's hard for the non-engineer to imagine how that would have any impact on landing an unmanned spacecraft or whatever on the moon. The effects seem to be too subtle to make that a valid selling point, as it were. So I'm obviously missing something.
Yeah. So I should say that this mission was selected completely on the basis of scientific merit. So this mission was not an exploration mission. It was the highest rated science proposal of the 24 or so that was received. But that said, look at what we've gone through in recent landings on Mars, where the error ellipses have gone, from being quite substantial to being very small, to the point where, with the Mars Science Lab, we're going to be able to put that lander down very close to the central peak of a crater that preserves the stratigraphy of early history of water. Okay, so on the moon after GRAIL, we now have imaging of the surface where we can resolve outcrop scale features, and if you want to land right next to a particular outcrop, you're going to be able to do it. Okay, so there will be no reason to do another gravity experiment of the moon in any of our lifetimes. If there's a particular sample return that we want to do, a particular reconnaissance in a particular area of the moon, you will be able to go exactly there and get it done.
Great. Any more questions here at Kennedy Space Center? All right. Well, thank you very much for joining us this morning. GRAIL Launch Day coverage, which is tomorrow, of course, weather willing, will begin at 6 a.m. Eastern on NASA TV as well as Ustream. For more information about GRAIL, please visit us on the web at www.nasa.gov/GRAIL or grail.nasa.gov. Have a good day.